The law of exponential growth and decay deals with a substance or population whose rate of change at any time is proportional to the amount of the substance present at that time. So what should catch our eye right here is this rate of change, because we know that that's calculus. That rate of change is what we've been working on this whole time. Proportional to means equal to. Before I go there, let me first recall for you y equals c times e raised to the kt power. This looks very much like PERT. C is going to equal our initial value. That's your starting amount. And we know that y is your end value. That's going to be some positive quantity. So we know it's the end value, but it's going to be a positive amount or positive quantity at any given time, t. K is our constant of proportionality. Constant of proportionality. We also know that as the rate, right? The rate at which our exponential function is increasing. And then t is our time. T is going to be any time t. Now what they're saying in this definition of law of exponential growth and decay, which is a definition that you have not heard of until now because you didn't really know calculus yet. The rate of change we know is dy dt. And the rate of change at any time is proportional to, so that's equal, proportional to the amount of the substance present at any time. So we're going to have our constant of proportionality times that positive amount, y, at any time. Now that we know enough about derivatives, we can come over here and we can further investigate where this is coming from. Y equals c times e raised to the kt power. So we take our derivative with respect to time, dy dt, is equal to our constant times the exponential expression e raised to the kt power times the derivative of that exponent, which would be k. Now, remember, this right here is just another way to say y. So we have dy dt is equal to y times k, which we also write as k times y. So that's where that comes from. That's where the definition comes from. That's pretty darn cool. Okay. Enough coolness. Let's do our first example. A sample contains 1 gram of radium. Will more than 0.5 grams of radium remain after 1,000 years? Radium has a half-life of 1,599 years. So we've got 1/2 remaining. If we start with 1 gram times e raised to the constant of proportionality times the amount of time. So 1,599 years later, if we start with 1, we'll have 1/2 remaining. 1,599 years later. It's a long time. It's a very long time. 1/2 equals e to the 1599 times k. I'm going to rewrite this in log form. So I've got log base e of 1/2 equals the exponent 1599 times k. I'm going to divide both sides by 1599. And the constant of proportionality for this problem, K, is equal to the natural log of 0.5. I'm going to write it as a decimal because I've run out of room. Divided by 1599. Now, will there be more than a half a gram remaining after 1,000 years? Yes, there is going to be more than a half remaining after 1,000 years because it's going to take almost 1,600 to get down to a half. But how much exactly will remain? Well, y is going to equal that 1 that we started with times e raised to the kt power. So k is the natural log of 0.5 divided by 1599, and our time is 1,000 years. Sorry for the paper scrunchling. That's another student in the classroom. I'm not going to mention any names, Bella. Y is approximately 0. Okay, I'm going to let you put this into your calculator. Hopefully I've waited long enough, otherwise you press pause because you really don't want me to just give you the answer because that ruins the fun. There's actually 0.645 grams remaining after 1,000 years. So the answer to this question is a big fat no. So will there be more than? No. But we kind of knew that already from the problem. But this allows us to explain how many there would be. I mean, will more than? Yes. Yes, more than will. I think I said no. I think I was distracted by the paper crumbling. Actually, that's just an excuse. I wasn't distracted by that. Yes, there's going to be more than a half a gram remaining because it's going to take 1,600 years until half remains. So, yes. Yes. More than half. Not less than half. More than half. Okay. Hopefully I got that right. Well, I know I got the answer right, but hopefully I didn't mess you all up. Okay, let's see if you can try the next one. It says determine the number of years for a 2-gram sample to decay to 1.3 grams. The half-life, important for you to know, for plutonium is 24,100 years. Okay, so I'm showing my work here. If we start with 2 and we end with 1.3, how much time is that going to be? So I'm going to divide both sides by 2. This is calculator intense. So we're going to have the natural log of 1.3 divided by 2. And then we're going to divide that by the k value, whatever this number is. And you should have gotten your time. That's equal to your time, and your time you should have gotten was 14,977.870 years. It's a really long time. It makes me want to sing the Big Bang Theory song. Although that doesn't even make a dent into 14 billion years ago, but it's 14,000 years ago, almost 15,000 years ago, or in the future. It all depends on where you're at. Okay, hopefully you understood this example, this try, and you're ready for the next.